Hey, good morning. How are you today? So you're excited for seeing more teams being qualified for the World Cup? Yes, Emma, I know you're very excited. Oh, Germany, your team is there already. Well, let's see which more teams will be there, and let's hope for the best and nice games. Well, let's speak some science. Today, we'll be speaking about the factors influencing the synthesis of zeolites. This is part one of the lecture, and next week we'll be having a continuity of it. Well, we have seen in the previous week that zeolites are the higher level of Lego constructions for chemists. We can create structures as small as 10 nanometers, which can withstand up to 1000 degrees Celsius. And in their synthesis, we saw that we start from silica, the main unit. Alumina can be also present, but it's not obligatory. And these primary building units can be transformed upon heat and with time to secondary building units, then these nice tertiary building units that gives us the final structures or the zeolites. Today, we will be digging into more details. We will see how to prepare these zeolites and to explore the different factors that can affect our synthesis. And also, I hope we will have the understanding that any small variation in the synthesis conditions can lead us to a different product than the one we are looking for. So if you're cooking at home, you know you will need a lot of ingredients, and so does the zeolite synthesis. We need different ingredients. Some of them, like the silica, is obligatory if you want to have a silicate or aluminosilicate. Alumina is also important, but it's not obligatory. You can build a zeolite without the presence of alumina. However, if you have alumina, you will need a mineralizing agent that helps in dissolving the alumina and silica and also act as a charge compensating agent, as we saw in the previous presentation or the previous week, that alumina needs something to normalize the charge and to have zero charge of the zeolite. We also have an important ingredient, which is called the structural directing agent. It is not part of the zeolite itself. However, it's like this wooden stuff you build around the house just to make the structure stable when constructing. And when the structure is done, you can just remove them or burn them out. These can be organic or inorganic, like sodium or other mineral agents. And also we use the water as a solvent, as when you are cooking any soup or liquid containing material, it helps in bringing the ingredients together and make the reaction mixture more homogeneous. Well, once you have all your ingredients and you mix them, you know we need several steps to go through. First, the zeolite is a very homogeneous structures, and you have to start by creating some nuclei. So when you prepare zeolite, you have to stir at room temperature. This will help to make some nuclei or source of the zeolites, points of origin, where the other ingredients will come and make the structure more structured and bigger. And also, when stirring, you homogenize the zeolite gel. You will have silica, alumina, SDA, all with equal concentration around each other. And then, after this is done, we go to something called the hydrothermal treatment. So you are heating under pressure in the presence of water. This is also called the crystal growth. So you have the nuclei, and now you are growing them to have your zeolite. Once the zeolite is done, if you are cooking at home, you can just eat. However, here we know it's a bit different because it's chemistry. So you have to wash out everything which is not in the structure. You may have excess silica, excess alumina, or some sodium that you don't want. You wash it out. And then to have your final structure, you have to calcine to burn the structural directing agent, or the SDA, which you don't need. It was there just to help in building the structure. Now we don't need it. Well, now we have our zeolite, but we have to be cautious that it is not a simple mix and heat. Any small modification in your zeolite synthesis, chemical or physical parameter will have a huge influence. For example, we spoke about silica and alumina. Do you know that the type of silica or alumina precursor you use will change the properties of your final product? You cannot start with a big precursor and you are aiming for a small structure. Same for Lego. You want a small structure, you start with small precursors. Then, how much of silica alumina ratio you are using? This can bring us to a different product that we will see in the next slide. Are you using a solvent? Are you using an inorganic or organic template? All this will differ. In terms of physical parameters, also, which one you are putting first? This will give us different properties. The one you will put first may be in the inside of the zeolite, and one you put after will be outside. Are you aging on it? Which temperature are you using? And how much time are you heating? All those can give an influence. In the coming slide, we'll discuss some of them, and next week we'll go for the rest. For example, in this tertiary diagram over here, if you read this way, you are looking at the silica. If you are reading this way on the alumina, and this way for the sodium hydroxide. For each point, it has silica, alumina, and sodium hydroxide content. And if we just look here, the silica is fixed, or here, the silica is fixed, but alumina and sodium are not. And each time we change the alumina, so we have put more alumina or less sodium, or the inverse, we have a different color, which means we are getting a different product. And for some of them, you can have a mixture of product, even it's not clean. And all this is because we changed a bit we introduced more alumina or less sodium hydroxide. And all those reactions were done at 65 degrees for 7 days. If we keep exactly the same concentrations, but only increase the temperature, from 65 to 100, look at the colors, all of them are different. Do you know what does it mean? It means that we have produced different types of zeolites simply by increasing the temperature. Well, is the temperature that important? Or even you can keep the same temperature but increase the time and you will change the zeolites. Well, to understand why do we have this, I have to tell you that zeolites are metastable materials. Their energy are very close. So if you heat them more, or you keep them for a longer time, they can jump from one stable structure to another structure, which is more stable at this temperature or this time. So if you need to have, let's say, the GIS zeolite, you need to know when to stop, because if you keep the reaction longer, it will go to another structure. And if you stop it before, you will end up with something different from what you need. So if you are preparing a zeolite, you need to refer to literature to see what people have done first to know where you can be. And also, if you have a structure, you need to know that this is the optimal conditions. Don't go far, otherwise you will ruin your experiment. Well, let's see what we have understood by today. Here are 4 questions. What are the main ingredients of the zeolite? What does it mean, zeolite as metastable materials? If you modify the silica-alumina ratio, does it influence on the final product? And can be zeolites, or a zeolite synthesis can result in distinct product if you keep it for a longer time? Well, let's see your answers. These are the true answers. Well, apparently all of you have the same answers. I can see from your papers up. Well, good. These are the main points that I wanted you to know today. And thank you for your kind attention. And see you next week when we speak about more and other factors that influence the zeolite synthesis.